Hello students, this is Naren Kumar Devedi once again welcoming you all in today's session. So today we will be covering numericals based on applications of Gauss's law. So let's begin with. So first question of today, a spherical conducting shell of inner radius R1 and outer radius R2 has a charge capital Q, a charge small q is placed at the center of the shell. First, what is the surface charge density on the inner surface and on the outer surface of the shell? Second, to calculate, write the expression for the electric field at a point x greater than R2, that means out of the second surface of shell from the center of the cell. So let me write the information given in the question. So first question, here the shell is comprising two surfaces concentric. One is say of radius R2, inner radius in the question given as R1, so I must take R1 as the inner radius center. Now outer radius, this is the outer surface, so on the outer surface I must have the radius to be equal to R2, small r2. This is the outer surface given in the question. Now, the Q charges are already there on the outer surface and small q charge is placed at the center of this shell. This is the question telling us. अब इसके बाद जैसे ही चार्ज को आपने सेंटर पे प्लेस किया शेल के, so due to the charging by induction, negative charges will be induced here in the inner surface of the shell, and just because of negative charges in the inner surface of the shell, the positive charges will be induced on the outer surface of the shell. So these are simply the induced charges that I am just drawing on the diagram. Okay, so now let's begin with first to calculate was the surface charge density in the inner surface. So that I am representing it by sigma I. So that is equal to, it is charge on the inner surface, that is minus q upon area of this sphere, that is 4 pi r1 square. Fine with this? So this is the inner surface charge density on this inner surface of shell. Now second is to calculate surface charge density on the outer surface. So on the outer surface, what are the total charges here? Already there was q, and this plus q charge is induced just because of charging by induction. So total charge is capital Q plus small q. So charge per unit area is of this outer surface. So 4 pi r2 square. So this is the first part of the question. Now for second part you must write. Second is telling us, write the expression for the electric field at a point x greater than R2. That means at certain point beyond this surface. So using Gauss's law, we can directly have this electric field intensity at a point say x, which is equal to 1 upon 4 pi epsilon naught. Now the total charge enclosed by the Gaussian surface, will be drawing the Gaussian surface enclosing this shell. So the total charge will be q plus small q upon distance square from the center, that is x square. So this is the required expression for the second part of the question. Okay, let's move on to have the second question now. We can have the second question with us now. See, electric field E equal to 100 Newton per Coulomb is shown in figure. Side of the cube is 20 centimeter. Find the nature of the charge which is inside the cube and the magnitude of charge. First, we must tell the nature of the charge looking at the diagram that is given in the question. And for the second part, we need to calculate the magnitude of that charge. This is the question. So the diagram given in the question is, this is the cube actually given, and here actually let me just draw the diagram. So this is the cube actually given in the question. Now here are the lines of forces on the diagram. Like this, these are lines of forces shown on the diagram, and the side is given to be 20 centimeter. This is the side given. Okay, fine. So as can be seen, electric lines of forces are coming outward of the cube. So obviously the charge inside the cube has to be positive in nature. So the first part we can write for the first part as lines of force are coming outwards, therefore the charge is positive. So the charge enclosed inside this volume is, inside this cube is positive in nature. Now for the second part we must calculate the charge magnitude of charge enclosed. So using Gauss's law now, Gauss's law, we have Q equals to epsilon naught into flux. Now flux will be the flux associated with this right surface and left surface. So we must have flux to be E into A plus E into A. So this one and this one. Only these two surfaces will contribute to the flux. So here, further moving ahead, we can write this to be, just place the values, 8.85 into 10 past 2 minus 12 into, this is 2 into E into A. So 2 into, the value of E given in the question is 100 Newton per second. So I am writing the value of E into area. Now area is, this is square. One face of the cube is square. So area of square is side square 20 into 10 past 2 minus 2 and it's square. So students, when you just solve it, you'll be getting approximately 7.08 into 10 past 2 minus 11 Coulomb. So this will be the answer that you'll be getting. Okay, so now let's have third question. The electric field in a region is radially outward with magnitude E equal to A into R. E equals to A into small r. Find the charge contained in a sphere of radius small a centered at the origin. Take A equals to 100,000 volt per square meter and small a equals to 30 centimeter. This is given information in the question. So just let me draw the diagram. Actually we don't need diagram, we directly we can go ahead. So electric field in a region is given. So directly we can have phi equals to, using Gauss's law, q by epsilon naught, and this phi we can write E into A is 4 pi r square times this sigma. So here we can have q. We need to calculate the charge contained in a sphere. Okay, so just placing this value of E here back, we have A into R with us, along with this 4 pi r square into this epsilon naught, now which is equals to small q. And one more thing we can have here, actually we can have this A into R square is A into R cube, and this 4 pi epsilon naught together, 4 pi epsilon naught, which is equal to q. Now see, this 4 pi epsilon naught has got value 1 upon 9 into 10 past to 9. So that we can directly have A is given to be 1000 and R is also given. So just placing the values, now we have 1000 as the value of A into R. Now actually this radius here is A. So radius, yeah, actually this A is the radius actually. So I must write, so that we don't have any confusion here, small r. So this value 30 in meters, it is 0.3 cube upon 9 into 10 past to 9, and this, students, when you solve it, you'll be getting 3 into 10 past to minus 9 coulomb as your required answer. So with this we can move ahead. So let me just have now next question with us, fourth. So fourth question, I'm just reading out. An electric dipole consists of charge plus minus 2 into 10 past to minus 8 coulomb separated by a distance of 2 into 10 past to minus 3 meter. It is placed near a long line charge of linear charge density 4 into 10 past to minus 4 coulomb per meter as shown in figure. I'll be drawing the diagram, such that the negative charge is at a distance of 2 centimeters from the line charge. Find the force acting on the dipole. Okay, so for the diagram, I must draw first diagram so that we can have a clear picture of the question. This is the line charge having linear charge density given in the question. I will be writing that separately. So from this, at 2 centimeter, there is the position of negative charge of dipole, and this is 2 centimeter. Now the dipole length is also given, positive charge of the dipole, and any more thing. So let me just write the information given. This minus q is 2 into 10 past to minus 8. This is plus 2 into 10 past to minus 8. And the separation between them is given to be 2 into 10 past to minus 3 meter given in the question. And here actually the line charge density that is given, negative charge lambda is given to be 4 into 10 past to minus 4 coulomb per meter. This is the information given in the question. We need to calculate the force acting. So here, how will I be proceeding? I will be first calculating the electric field here due to this line charge. Now thereafter, force at this minus q charge of dipole, F equals to q into E. Later on, the electric field due to this at this position, and thereby multiplying that electric field with this charge will be having force. And just by applying superposition principle, we can have the total force acting. Okay, so let's proceed now. So here the electric field at minus q charge, let me call it E1. So this is equals to lambda upon 2 pi epsilon naught into R. R is what? Actually the distance. So just now placing the values, we can have here one more thing. We can just to have the simplification, just multiply and divide it by 2 so that a constant value is with us, 1 upon 4 pi epsilon naught 2 lambda by R. So this makes 9 into 10 power to 9 into that 2 into this lambda 4 into 10 power to minus 4 upon this distance is 2 centimeters. So that 2 centimeter is approximately 2 into 10 power to minus 2 meter. Okay, so now students, when you solve it, you'll be getting approximately this 3.6 into 10 power to 8 Newton per Coulomb. So this is actually the electric field intensity due to this line charge at this position. Okay, now force, we can have force F1, which is equals to Q into E, and that is equals to, what's the charge of dipole? It's 2 into 10 power to minus 8 given in the question into this electric field 3.6 into 10 power to 8. So this as you solve it, you'll be getting 7.2 Newton. And what's the direction, students, of this force? It is towards the line charge. So you must clearly mention the direction towards the line charge. So this is half done. We are half done now. Now we'll be calculating electric field here due to this line charge, and thereby multiplying that with Q will have force. So similarly E2 will be equals to 9 into 10 power to 9 into that 2 into 4 into 10 power to minus 4 upon, now distance. See, distance would be 2 centimeter plus this. So here the distance you will be getting 0.022 meter. Fine with this? Thereafter, students, just solving it will be getting actually approximately 3.3 into 10 power to 8 Newton per Coulomb. This is actually the electric field intensity at the position of plus Q charge. Now force F2 equals to Q into E2. So this is charge would remain same, Q2 into 10 power to minus 8 into that 3.3 into 10 power to 8. So just having the simplification of this, you'll be getting, students, 6.6 Newton. Now what's the direction of this force? This is plus charge, positive charge, away from line charge. Okay, so now we can have the superposition principle, and thereby we can have the total charge, the net charge, net force F equals to, now see, this is greater in magnitude and this is lesser in magnitude, so let's calculate along this direction. So this is 7.2 minus 6.6, so you'll be getting 0.6 Newton, and what will be the direction along this? Towards the line charge. So actually this is the proper solution of this question. Okay students, so let's have the next question with us. Fifth question. A particle of mass 5 into 10 power to minus 6 gram is kept over a large horizontal sheet of charge of density 4 into 10 power to minus 6 coulomb per square meter. What charge should be given to this particle so that if released, it does not fall down? How many electrons are to be removed to give this charge? How much mass is decreased due to the removal of these electrons? So this is the question that is demanding the answer from us. So fifth question, mass of particle is given to be 5 into 10 power to minus 6 gram, or you can have 5 into 10 power to minus 9 kg. Thereafter, charge density, surface charge density is given to be 4 into 10 power to minus 6 coulomb per square meter. Let me just have the diagram so that we may have better idea. So this is actually the plane sheet of charges having uniform distribution of charge, and here a particle is kept. So when released, what charges are given? So we'll be assuming let Q charge is given to this particle. So when released, so this line S, surface charge distribution on this sheet, will apply vertical force, and that force will be balanced by the weight of this, and that will be in equilibrium position at rest. So for the equilibrium, what do we have? Force due to this has to be equals to weight, and here we can have this mg upon E and mg upon electric field due to the sheet. It is sigma upon 2 epsilon naught. So we can have here sigma upon 2 epsilon naught. Now see, this 2 epsilon naught goes up, and this makes 2 epsilon naught into mg upon sigma. So this is the formula with us. Now you can just place all values and have the answer. So just let me place the values. 2 into, it is 8.85 into 10 power to minus 12 into, hereafter we can have this mass is given to be 5 into 10 power to minus 9. Gravity, we have 9.8 with us, upon sigma it is 4 into 10 power to minus 6. So here actually students, you can have the final outcome to be 2.21 into 10 power to minus 13 coulomb. So this is the charge that needs to be given to that particle so that if released, that remains static at rest, does not fall down. Okay, so now let's move on. The second part of this question is demanding from us how many electrons are to be given to make this charge. So using quantization now, Q equals to Ne, we have Q to be 2.21 into 10 power to minus 13 upon charge on electron 1.6 into 10 power to minus 19. So that is going to give us the value of N, and this value will approximately be coming out to be 1.4 into 10 power to 6. This will be the number of electrons to be given to make this much charge. Okay, now moving ahead, how much mass is decreased when these many numbers of electrons are removed? So mass decreased equals to, you simply just multiply this number with mass of one single electron. So you will be having 1.4 into 10 powers to 6 into that 9.1 into 10 powers to minus 31 kg, and this simply will give you 1.3 into 10 powers to minus 24 kg. So this is the last answer for the question. Okay, students, so now let's have sixth question. Consider following very rough model of a beryllium atom. The nucleus has 4 protons and 4 neutrons confined to a small volume of radius 10 powers to minus 15 meter. The two 1s electrons make a spherical charge cloud at an average distance of 1.3 into 10 powers to minus 11 meter from the nucleus, whereas the two 2s electrons make another spherical cloud at an average distance of 5.2 into 10 powers to minus 11 meter from the nucleus. Find the electric field at first a point just inside the 1s cloud, and second a point just inside the 2s cloud. Okay, so let me just draw this question on the diagram so that students, you can have better understanding. This is actually the inner sphere representing the nucleus. So here I must write N, nucleus, and nucleus of beryllium atom, and this is actually 1s orbit forming the cloud, and this is actually 2s orbit forming another cloud. So the this radius is given to be 10 powers to minus 15 meter nuclear size, and this 1s, actually I must write this to be 1s and this to be 2s. So this 1s is given average distance of 1.3 into 10 powers to minus 11 meter, and this second one 2s, this is given 5.2 into 10 powers to minus 11 meter. This is second cloud. Okay, so we must find first electric field intensity at a point just inside the 1s cloud. So somewhere here inside this 1s, somewhere here, let me call this point to be P. So the average distance we will be taking from the nucleus of this point to be 1.3 into 10 powers to minus 11 meter. So actually this is the question. So let's begin the solution for the first part. So we must first have the charge. So the charge, let me call this to be A, this to be B, and this to be C. So we'll be writing charges on A, B and C. So the charge on A, which is equals to, so the nucleus has got 4 protons given in the question. Fine. So 4 into charge on 1 electron, 1.6 into 10 powers to minus 19 coulomb, and this similarly charge on B. So B has got 2 electrons. The two 1s electrons make a spherical charge cloud. So here we can have 2 into 10, 1.6 into 10 powers to minus 19 coulomb, and the charge on this 2s, again there are 2 electrons given in the question, 1.6 into 10 powers to minus 19 coulomb. So these are simply the charges on different orbits along with this nucleus. So here now we write the electric field the electric field at P, which is just inside the 1s spherical cloud. So here we write E equals to 1 upon 4 pi epsilon naught into Q by R square. So here let's place the value 9 into 10 past to 9. Now charge on this 1s. So charge on that 1s is given to be 4 into this 1.6 into 10 past to minus 19 upon, what's the distance? As I said, distance will be taking this 1.3 into 10 past to minus 11 and this much square. So actually this is the first solution of first part of the question. Okay, so students, you just try to solve it by your own. So as you solve it, you'll be getting the answer approximately 3.4 into 10 past to 13 Newton per Coulomb as the electric field intensity. Okay, now for the second one, on B part, electric field intensity at a point just inside this 2s. So inside this 2s, we must first have the charge enclosed by this 2s surface. As this has got certain charges and this has got certain charges, so the total charge bounded by this 2s we must have, enclosed by 2s we must first have. So we must write now the charge enclosed by 2s. It is actually this 4 into this minus this. So 4 minus 2 into 1.6 into 10 past to minus 19, and this is going to give us 2 into 1.6 into 10 past to minus 19. So these are simply the charges which are enclosed by this 2s spherical cloud. And the distance from the nucleus is already given to us. We can directly apply the formula. Therefore, E equals to, this is 9 into 10 past to 9 into charge. Now charge is 2 into 10 past to, 2 into 1.6 into 10 past to minus 19 upon distance square. So distance given 5.2, this one, into 10 past to minus 11 its square. So students, just solve it. You'll be getting approximately 1.065 into 10 past to 12 Newton per Coulomb as the answer. So this makes the completion of solution for the question. Okay students, let's have next question, 7th question with us. A long cylindrical wire carries a positive charge of linear charge density 2 into 10 past to minus 8 Coulomb per meter. An electron revolves around it in a circular path under the influence of the attractive electrostatic force. Find the kinetic energy of the electron. Note that it is independent of the radius. So let's start solution part, 7th question. Let me draw the diagram. So this is actually the line charge given and an electron revolving around it in a circular path. So here the cylindrical hypothetical Gaussian surface will be seen enclosing this charge, line charge distribution. So here the electric field, because see that force given by this line charge to that revolving electron will be equal to the centripetal force required by the electron to move in the circular path. So for that we must have electric field with us. So electric field at a certain point due to this line charge lambda upon 2 pi epsilon naught into R. So here you can write it 1 upon 4 pi epsilon naught into 2 lambda by r. So this value is 9 into 10 power to 9 directly into 2 into lambda given in the question is 2 into 10 power to minus 8 upon, what's the distance now? Distance given here is actually, okay, so here actually the distance given to be, let it be r, because distance is not clearly mentioned in the question, and one thing is given that kinetic energy remains independent of the radius. So radius somewhere will get lost, but will get cancelled. So let me continue with this r here. So thereafter actually since QE will be equals to centripetal force mv square by r. Okay, so now just cross multiplying this r over here and placing the value of E back here. So it is 2 to the 4, 4 9 to the 36, 36, and this is 0, 1, 10 will remain. Upon this r, this is actually, now this r goes in multiple, which is equals to mv square. So r and r will get cancelled, and charge on electron we are aware of 1.6 into 10 power to minus 19 into this 360. One more thing we can have multiplication of half on both the sides. So this right hand side term becomes the kinetic energy that we need to calculate. So it is Ke simply, and students, when you solve it, so you'll be getting final outcome 2.88 into 10 power to minus 17 joule. So this will be your required answer. Okay, so let's move on. So students, let's have the last question, 8th one. One end of a 10 centimeter long silk thread is fixed to a large vertical surface of a charged non-conducting plate, and the other end is fastened to a small ball having a mass of 10 gram and a charge of 4 into 10 power to minus 6 coulomb. In equilibrium, the thread makes an angle of 60 degree with the vertical. Find the surface charge density on the plate. This is the question. Okay, so let's move on. 8th question. Let me just draw the diagram so that we can have a brief idea. So here charges are there, non-conducting plate is there. So it is this region, and somewhere with the vertical surface, the one end of the silk thread is fixed and the other end is fastened to a ball, spherical ball having certain mass 10 grams somewhere, if I am not mistaken, given in the question. So here actually with the vertical, this silk thread is making 60 degree angle. So this is the tension acting towards the rigid support. Now here, if we just resolve this tension, this will be 60 again, theta let me call, that will be just equal to this 60. So this will be T cos theta, and here mass will act vertically down. Now here it is T sin theta, and just because of this charge and this ball which is also charged will experience force due to the electric field of that. So this will be around this. So in equilibrium, we can write actually T sin theta will be equals to just QE, and T cos theta will be equals to this mg. So just now having this division, we can have this tan theta. So tan theta will be equals to QE upon mg, and this E, electric field due to the sheet, charged non-conducting sheet, we can have Q into sigma upon 2 epsilon naught mg into 2 epsilon naught. So now here actually we must have sigma. So just transposing, cross multiplying rest of the things. So sigma value we can have 2 mg into epsilon naught into tan theta upon this Q. So now values given in the question, 2 into mass is 10 gram, 10 into 10 power to minus 3 into 9.8 into this value 8.85 into 10 power to minus 12 into tan 60. Tan 60 is root 3, 1.732 divided by charge given 4 into 10 power to minus 6 coulomb given in the question. So students, just go on solving this. You'll get approximately 7.5 into 10 power to minus 7 coulomb per square meter as your final outcome. So with this we end up today's session. So students, I hope you have enjoyed numericals. So do like and subscribe the channel.